deep learning. If we start talking about deep learning, we have to understand what is AI, what is machine learning, and what is deep learning. And AI is a branch of computer science focused on creating systems capable of performing tasks that would normally require human intelligence. But this include activities like decision making, learning, virtual perception, language processing. AI aims to mimic human reasoning and logic to solve complex problems and automate repetitive or dangerous tasks. Modern AI systems can be found in applications like autonomous vehicles, recommended systems, and chatbots, etc. And if we talk about machine learning, ML is a subset of AI that deals specifically with the development of algorithms that enable computer to learn and improve automatically through experience without being explicitly programmed. It is focused on pattern recognition, prediction, decision making based on data. Unlike traditional programming where logic is hard coded, ML algorithms evolve and adapt, learning from vast data set. And if we talk about deep learning, it's a subfield of machine learning, inspired by the structure, functionality of human brain's neural network. It leverages hierarchical architecture to learn from data by automatically extracting features, representation at various levels of abstraction. Deep learning excels in tasks such as image classification, speech recognition, language modeling, and thanks to ability to handle unstructured and high dimensional data. And if we talk about historical background, it started during in 1950s to 1970s, where AI research began with symbolic AI and rule-based systems such as logic theorist and gene problem solver, and focused on solving problem using explicit rules and heuristics. And emergence of machine learning started during in 1980s with the rise of statistical models, neural network, and concepts like back propagation. Machine learning gained momentum. Algorithms such as decision tree, support vector machines emerged and emphasize data-driven learning. And if we talk about deep learning revolution, it started around 2010s. Advance in hardware like GPUs and TPUs, access to large data set, novel architecture like convolutional neural networks, that's also called CNNs, led to deep learning boom. A breakthrough in areas like image classification, AlexNet, NLP like BERT, GPT solidified its position in AI research. And if we talk about significance of deep learning in modern AI, so deep learning has transformed AI by enabling machines to process vast quantities of unstructured data such as image, audio, text with remarkable accuracy. Unlike traditional machine learning, which relies on feature engineering, deep learning systems learn features automatically. And major breakthroughs in fields like computer vision, speech recognition, and NLP had led to uh, real world applications including self-driving cars, automated translation system, and voice assistants. And its ability to generate complex patterns has made deep learning indispensable in industries like healthcare, specifically in medical diagnostic, finance, fraud detection, entertainment recommendations systems. And deep learning also serves as the foundation of emerging AI trends such as generative models, for example, GNS, GANs, and large language models that is called GPT. And moving forward, if we talk about fundamentals of deep learning, uh, it has neural networks, which are the building blocks. That's also called the uh, pers- perceptron model. The perceptron model introduced by Frank Rosenblatt in 1958. It is the simplest neural network model consisting of single layer of neurons. It performs binary classification by applying linear transformation to input features, a threshold based activation function. However, its inability to solve non-linear problem limited its early adoption. And then is multi-layer perceptron, that is called MLP. It extends the perceptron model by adding hidden layers between the input and the output layer. These hidden layers enable the network to learn non-linear mapping between the inputs and the output. MLPs are fully connected, meaning each neuron in one layer is connected to every neuron in the next layer. And then is the neurons and the weight. Each neuron receives weighted output and applies an activation function and passes the result to the next layer. The weight adjusted during training to minimize prediction errors, making them core learning mechanism. And the importance is neural networks are the backbone of deep learning. As the number of layers increases, so does the network ability to learn hierarchical representations of data. And in terms of the activation function, uh, uh, it introduced non-linearity into neural networks, allowing them to approximate complex mapping from input to output um, without the entire network. They have to behave like simple linear model. So one is like sigmoid function, and another is a sigmoid function maps any real valued number to a value between 0 and 1. It is commonly used in binary classification problems, or it suffers from the vanishing gradient problems, making it less suitable for deep networks. And then is ReLU, rectified linear unit, which is most widely used activation function in modern deep learning models. It outputs the directly if positive and zero otherwise. And then is 10f function, which maps values to a range between -1 and 1, providing zero-centered output, which can help with convergence. And then is loss function. Loss function measures the discrepancy between the model's prediction and the actual target value. Choosing the right loss function is crucial for the model performance. So first is like mean squared error, MSE. It's commonly used for regression task, measures the average square difference between the predicted and the actual value. And then is cross entropy loss, which is used in classification tasks to quantify the difference between predicted probability distribution to the true distribution. So it is particularly effective in multi-class problems, guiding the model to output high confidence scores to the correct class. And if we talk about optimization techniques, uh, it aims to minimize the loss of function by adjusting neural parameters during training. Then is gradient descent, which updates the model parameter in the direction of negative gradient to the loss function. The step size is determined by the learning rate. However, it has some challenges, like choosing an appropriate learning rate is crucial to avoid slow convergence to overshooting. Then SEGD, which is stochastic gradient descent. Unlike the standard gradient descent, which computes gradient using entire dataset, SGD updates the parameter using small batches of data. This makes computationally efficient and suitable for the large dataset. Then is Adam Optimizer, which combines the advantages of momentum-based optimization and adaptive learning rates. It, it maintains the running averages of past gradient and scared gradient to the uh, adjust the learning rate dynamically. And the benefits are like faster convergence and robustness to the hyperparameter tuning. And if we talk about back propagation and training process, first one is like forward propagation. In the forward pass, the input data is passed through the network. Predictions are made based on weight and biases. And if we talk about back propagation, which computes gradients of the loss function with respect to each parameter, using the chain rule of differentiation. These gradients are propagated backward throughout the network. And then is like weight updates. These the gradients are used to update the model parameter, weights, and biases through the optimization algorithm like STD or ADAM. And in terms of iteration, this process is repeated for multiple iterations, which is also called epochs, until the model converges or achieves satisfactory performance. Moving forward, deep learning architecture. The first one is feed forward neural networks, FNNs. So the structure is like feed forward neural networks are the simplest type of neural network architecture, wherever the information flows in one direction from the input layer to the output layer. There are no cycles or the loops. However, if we talk about hidden layer, FFN may contain multiple hidden layers which uh, with each layer learning intermediate representation of the input data. The applications are like used in simple classification regression problems where input and output mapping do not require any memory of past input. And if we talk about convolutional neural networks, CNN, the purpose is they are specifically designed to process data with spatial hierarchies such as images, videos. They excel in tasks where the patterns and the spatial relationship matters. And if we talk about their key components are like convolutional layers, pooling layers, fully connected layers. And the applications, as I mentioned, image classification, for example, image net, object detection, and image segmentation, that is UNet. And if we talk about recurrent neural networks, for this, RN are designed to handle sequential data by maintaining the memory of previous input. They are commonly used in tasks where it is important, like language modeling, time series forecasting, or speech recognition. And if we talk about at autoencoders, the purpose is autoencoders are unsupervised learning models used for dimensionality reduction, feature extraction, anomaly detection. They learn to compress input data into lower dimensional representation and then reconstruct it. An autoencoder consists of encoder which compresses the input and decoder which reconstructs the input. The bottleneck layer between them captures the essential features. And if we talk about generative adversarial networks, GANs, the main purpose they are used to generate realistic data samples such as images, videos, audios. They consist of two neural networks trained simultaneously in competitive setting. And and if we talk about the architecture, the generator network creates fake data samples while discriminator networks attempts to distinguish between real and generated samples. The goal is to make discriminator unable to tell the difference. And if we talk about transformer models, the main purpose is they are basically the foundation of modern natural language processing models, enabling breakthroughs in tasks like translations, text summarization, question answering. The attention mechanism allows the model to focus on relative part of the input sequence, enabling it to handle long range of dependencies efficiently. And in terms of architecture, unlike RNNs, a transformer process the entire input sequence simultaneously and using the multi-head self-attention and feed forward layers. And in terms of moving forward, uh, the training of deep learning models uh, we normally start with the data preparation, the first steps like data cleansing, removing all the errors, inconsistencies, noise from the data, ensure quality inputs. And then is data normalization, which is scaling feature to a common edge to improve convergence during training. And then is data augmentation, which is the increasing the size and the diversity of the training data set through transformation like rotation, flipping, cropping, especially for the images. And if we talk about completing data, training, validation, and testing the set, the purpose of the splitting the data ensures the model is evaluated or unseen data, reducing the risk of overfitting. And it's do like validation techniques like k-fold cross validation improve the robustness of the model performance estimation. And we have to make sure we are choosing the right model architecture. Specifically, we have to think about architecture selection, which is like matching the problem type with an appropriate architecture. For example, CNN for images, transformers for text, and regularization techniques that prevent overfitting through dropout, weight decay, and early stopping. And if we talk about hyperparameter training, tuning, in this, the key hyperparameters is like learning rate, batch size, number of layers, and activation functions. And the search models are like grid search, random search, Bayesian optimization for finding optimal parameter configurations. And in terms of training and evaluation metrics, the classification metrics are like accuracy, precision, recall, F1 score, ROC, AUC, and they have like regression metrics as well, which is like mean squared error, MSE, and mean absolute error, which is MAE, and the R squared. And if they're like, as we know, there are like number of challenges in deep learning as well. So first is overfitting and underfitting when the model learns noise and specific patterns from training data. So it leads to the poor generalization or the unseen data. And underfitting is like when the model is too simple to capture the undenying patterns, resulting in poor performance on both training and test data. So the solution for this is like regularization, dropout, data augmentation, model complexity, tuning that can help mitigate these issues. And then is data scarcity. That a deep model require large amount of label data, which can be expensive, time consuming to obtain as well. And the solution is transfer learning, data augmentation, synthetic data generation, or semi-supervised learning. And if we talk about computational complexity, the training deep learning model is resource intensive, often requiring GPUs, TPUs. So for this, distributing training, model pruning, quantization, help that can optimize the computational resource. And then is interpretability and explainability. So in terms of like black box nature, deep models are often difficult to interpret, making it challenging to understand their decision making process. So techniques like SHAP values, LIME, which is local interpretable model agnostic explanations, attention mechanism can provide insight into the model behavior. And in terms of the advanced topics in deep learning, the first is like transfer learning. The purpose is like leveraging the pre-trained model on related tasks to improve performance and reduce training time. The popular pre-trained models are like RESNet, VGG, BERT, and all we know like GPT models. The applications are like image classification, NLP, speech, etc. And thank you so much for watching. Please like and subscribe and let me know in the comment. Thank you. Have a good one.